going to talk about OpenWRT integration for AP-NOS. So first things first, most important slide. In the industry, everyone writes OpenWRT with a capital R and a capital T. That's actually incorrect, and I've been asked several times to present this slide. It's written with a small r and a small t. OpenWRT originates from the WRT54G, pretty well-known device, even hit South Park. It's been in several comics and memes. So yes, what's OpenWRT? This is taken from the OpenWRT webpage. Most of you will know OpenWRT. It's one of the most commonly used open source embedded Linux distributions. Currently, we support about 2,000 different devices, wide variety. There's ADSL modems. We've had handhelds, NAS systems, PDAs. Most commonly, obviously, it's access points, right? Primary focus are Qualcomm and MediaTek drivers. There's limited implementation for Broadcom. So why use OpenWRT? So this is, again, marketing text taken directly from the OpenWRT webpage. It's really a personal choice that you need to take. How much open source do you want to do and how much vendor lock-in do you want, right? The more open source you want, the more flexibility you want, the more you should be inclined to use OpenWRT. So OpenWRT targets. We support a wide variety of CPU architectures, so commonly used ARM, MIPS, x86, PowerPC. OpenWRT splits up the build system into targets and sub-targets. So targets are typically your SoCs, SoC vendors. So we have 38 different system on chips that we support. Each one of them can have multiple sub-targets. So a vendor would produce one kind of silicon and have multiple different, very similar versions. An example of this would be MediaTek with the MP7623, then the 22 and the new Phi Logic. They're pretty much all the same with slight variations of the actual IP blocks inside the silicon, right? There are also several OpenWRT ports out in the industry by vendors which aren't really upstreamed. These can be heavily patched versions of OpenWRT, might even include own patched versions of GCC and the toolchain. So how does upstreaming work? The way OpenWRT works is that we try to write as little patches or hold as little patches as possible with us and carrying them around. So we take an upstream version of a package, and with that we track our local changes. We don't want to fork packages, right? Forking a package means that you have to do the maintenance for the next few months, years, whatever yourself. This is kind of the same approach that the Linux kernel works. So you have the upstream Linux tree, then you have your subsystem maintainers, you have your contributors, they all have staging trees, and you try to push changes upstream and get newest versions downstream from down to your version from upstream as soon as possible, right? So there's a bidirectional flow of changes. So ideally we just track local fixes, new features, try to get them upstream as soon as possible, and then with the next version, changes trickle back down. There's one special case, which is the Compat wireless backports, right? So quite commonly, you will have slightly outdated kernels due to stability issues. You want to, kernels tend to need a little bit of time until they are mass production stable. However, you want to be able to use latest Wi-Fi. So there's a lot of changes going into the Wi-Fi stack. So there's a thing called Compat Wireless, which is used by not just OpenWRT, it's very commonly used by most normal Linux distributions. So imagine you have your enterprise Red Hat Linux, they have their 4.19 kernel. They offer long-term support for this, but going forward 2 years later, you want to be able to run latest Wi-Fi hardware on those releases. So that's what Compat Wireless is. Compat Wireless is a way to take the latest 5.15, 6.0, whatever kernel, and integrate the Wi-Fi stack, Wi-Fi drivers into an older 5 series or even 4 series kernel, right? If you look at a vendor SDK, what we see normally is that the baseline version of OpenWRT tends to be heavily outdated. So quite a few vendors right now will actually ship a 2014 or 2019 version of OpenWRT, although there's a 2022 is the latest version. Even worse, if the OpenWT version might be outdated by like 5 years or something, quite a lot of the vendors will actually ship a kernel that can be outdated by 8 or 9 years, right? That's unfortunately the hard reality. And these kernels tend to be hard forks, right? So big silicon vendors will take a Linux kernel at some point, they will stick with that version for 4, 5, 6 years. At the end of life of that kernel version, they will have patched 100,000, 200,000, sometimes even more lines of code onto that kernel, making it really hard to rebase. So when they go to a new updated kernel, they actually have to redo the entire work, and big silicon vendors can take up to a year, maybe even 2 years to update their kernel version and get it internally GA qualified. Yeah, so what does TIP do to avoid this problem of hard forking, right? Forking is always bad. You never want to fork if the moment you start forking your software, you've already lost. So we use the same logic in TIP OpenWiFi that we see in OpenWT with staging trees, right? So we take the latest version of OpenWT as baseline. We have local staging branches, so we consider TIP OpenWiFi a staging area for features getting integrated into OpenWT. We build patches locally, apply them on top of the baseline, send them upstream. Some of the patches and features that we actually built inside OpenWiFi, we actually developed and tested inside OpenWT. And when they were upstream in OpenWT, we actually ported them back to TIP OpenWiFi. So in some cases, we didn't even put them in OpenWiFi first, but they went directly into OpenWT. Yeah, so kernels and drivers. So in an ideal world, you build a product, you take latest Linux kernel, has all the Wi-Fi drivers in it, you're happy. Reality is, if you want to take turnkey solutions, latest Wi-Fi when Wi-Fi 6 came out, you were stuck with having to use a vendor kernel, vendor Wi-Fi driver. If you go into things like PON and so on, it gets even worse. DSL was also a big problem at the time. We can go and say, let's take your Qualcomm SDK, right? You'll have your 2015 OpenWT, your 4.4 kernel. Right now, we can't really get around the 4.4 kernel. Okay, there's a 5.4 which still has problems, but we're kind of stuck with the old kernel. What we can do, however, is we can extract all that kernel stuff, the driver level stuff, and integrate it ourselves into more recent OpenWT, right? So this is what we've done. We said across the entire portfolio of all of our devices, we'll use latest OpenWT with TIP OpenWiFi stuff on top of it. And we'll have to, unfortunately, build a target feed and use the proprietary forked version of the kernel, right? So what does this include? You'll be stuck with the actual baseline kernel, would be 4.4, then typically you will have your wired interface drivers, you'll have your, low pin count peripheral, thermal sensors, GPIOs, watchdogs, that kind of stuff. And then obviously the Wi-Fi. Wi-Fi tends, although it's actually the biggest chunk of work, is actually the easiest because those vendors will use what I described earlier, and they'll use the backport packages, right? So if Qualcomm wants to use a 4.4 kernel, but they want to use Wi-Fi 6, they are stuck with actually having to use something like a 515 or whatever subsystem, because 4.4 simply didn't even know what Wi-Fi 6 was. In addition to the actual driver, there's also silicon dependencies, right? So a lot of open source developers will tell you everything has to be open. The reality is it's simply not that way, especially moving into far higher data rates. We have pseudo real-time requirements, right? So obviously there's the ARM Trust firmware. Some vendors will actually open up the source code and allow us in open source to recompile it ourselves. Then you have like the three big usual suspects. One is the Wi-Fi firmware. This can be a huge blob. Some of the vendors would actually have a megabyte or even larger firmware that they load into the WMAC. Then in Qualcomm case, you have the NSS firmware, which is the network subsystem, which is kind of their hardware acceleration and offloading subsystem. So Wi-Fi 5 and Wi-Fi 6 silicon from Qualcomm had a quad or dual core Ubicom 32 real-time network operating system inside the SoC, which actually handled the offloading. And then obviously with higher data rate physical PHYs, like a Quencher's classic one, they'll actually have a firmware that you need to load as well. And they'll see regular firmware updates. So those are the 3 files which, when we update to newer vendor kernels and SDKs, so can be a little bit annoying because you have to convince the vendors to actually put these files under redistributable licenses somewhere on GitHub. If you take a Qualcomm SDK, for example, the NSS normally gets installed in a separate UBI volume so that you can upload and redistribute new firmware images which don't actually include the NSS firmware, right? So it's always a little bit of a hurdle to convince vendors to make all that stuff redistributable. Then there are some more things. You have something called the board definition file. So board definition file is a way that vendors describe a specific SKU's RF behavior. So this would be stuff like the SKU has, I don't know, the antennas are +3 dB or +5 dB or something. Those are the BDF files. And then you will have per board-specific calibration data as well, right? So the calibration data is the actual variance in electronic components on that specific board. So those boards get calibrated. Yeah. As I said earlier on, you have patches, right? We don't want to modify source code directly, so we modify source code by tracking the upstream version of source and patches. Over time, the number of patches that you have can grow, and you need some tooling to work with this. So there's this great tool called Quilt. This is a tool which you will find that most major Linux distributions will use, right? If you look at Debian, Red Hat, whatever, they all have a wiki page explaining how to use Quilt. OpenWRT's build system has pretty handy tools built in, so we can see if we run make package example and then quilt equals to 1, we'll actually unpack the source code, apply all the patches, set up quilt, and then you have tools go into the build folder, and then you can push and pop and traverse up and down your stack or your chain of patches, modify patches, add new patches, remove patches, refresh patches. This is a very handy tool for distribution maintainers to be able to deal in a clean manner with patches. There's a great link to the wiki in OpenWRT, which explains this as well. For anyone who's a developer and does distribution maintenance, this is one of the most important tools you have and should use regularly. So managing kernel patches is pretty much the same as with packages, right? OpenWRT goes a little bit further, so we don't just have a patches folder, but OpenWRT will have 3 folders. One is backports, pending, and hex, right? So backports is basically, we are currently on kernel 5.4 or something, and we found an issue, and this was actually fixed in 5.8. So we can take that specific fix from the 5.8 kernel, import it into our backports folder, keep it there until we ourselves update to 5.8 or newer, and then once upstream already includes this backport, we can drop the patch. Pending is any patch that we've found, issue that we've identified, things that we've sent upstream, and this stuff is currently in the queue going upstream, or we're waiting on the newest update locally with that patch for us to trickle down. And then hex will be any patch that we carry locally, which is simply not viable for going upstream, right? These could be build system specific things. There are a couple of size optimizations, performance optimizations, which we specifically do for embedded devices. Because of that, they're simply not viable for upstream. And then for the developers, there's similar to the previous slide, the examples of the commands that you have to do to unpack and prepare kernel using the Quilt build system. Okay, so that was dry theory on OpenWRT. Now we're actually getting into TIP APNOS, right? So Chris already mentioned this earlier on. If you look at a vendor SDK, they will take an OpenWRT, import it into their local Git. They'll patch left, right, center across the entire branch, and they will give you the pre-patched version of OpenWRT, right? We don't want to do that because it's just complete maintenance nightmare. So what we do in the top right, you see a YAML file, and we'll just say, okay, this is our baseline Git repository for OpenWRT. This is the branch. This is the commit hash. And then we have a list of folders with patches that we want to apply on top of it, right? This way, when we go to a newer version, we can basically just say, okay, go to a different version of OpenWRT, and then we can apply the patches. We can rebase them manually, make sure that the ones which have already gone upstream can get removed. What we saw, this is slightly, maybe 2 months old, this image. So we recently updated to 2203. We were on 2102 pretty much since it launched last year. We gathered about 120 patches inside TIP OpenWiFi. When we updated to 2203, we managed to delete almost 80 of those because we'd already upstreamed 2/3 of the patches into OpenWRT, which is basically shows it was the right decision to work this way, right? So there's a Python tool called setup.py. Setup.py will read this YAML file, clone the OpenWRT, and then use git auto-merge to apply the patches from our patches folder. Yeah, and then we'll do an update on the feeds and set up the basic build environment. There's a second tool called generate config. This is now inside your checked out and pre-patched version of OpenWRT. That's the bottom right. Those are device-specific profiles. So device-specific profile defines this is the name of the board and the target inside OpenWRT that I want to build. You can then add multiple feeds or includes of packages that you want. In our case, this would be the in this case, this is an EAP 101 from EdgeCore. We're basically saying, okay, we need to have the target feed for the Wi-Fi 6 Qualcomm silicon. We need to have the feed for the backports for Wi-Fi 6 from Qualcomm. There's a Bluetooth chip in there, so we load the packages, and then there we include the uCentral AP feed. uCentral AP feed is yet another profile of YAML file, and that has a long list of all the different tools and features, the client that we use for the WebSockets, handling DigiCert certificates, and rate limiting, captive portal, like all the cool features that we have. Yeah, you run generate config.python, pass it that YAML file. Output is a typical kbuild.config file in your folder, and that's your OpenWRT system set up in a way that can directly build an image for this specific board with that specific OpenWiFi uCentral configuration. The CI that Chris mentioned will actually run our 30 or whatever different YAML files, generate 30 different trees, and build the images. Yeah, so how do we build an image? This is very developer specific. OpenWRT uses the kbuild infrastructure from the Linux kernel. So on the bottom you can see one is OpenWRT, the other one is the default menu config from the kernel. As you can see, it's very hard to tell the difference between which is which. The build system is pretty much identical. You have your .config file, you can do make menu config, you can manually edit stuff if you want, and then you simply do make or make -J8 or VSCS or the usual how make works. Resulting images will be in the folder bin targets, and you'll have your targets and sub-target folders in there, and that's where your final sysupgrade and init.ramfs images will be located. Yeah, so how does communication between services on OpenWRT actually work, right? We have a thing called UBus. UBus is a very integral IPC tool inside OpenWRT. Any service that is OpenWRT specific will talk UBus. Even the services amongst each other will talk UBus. UBus is essentially a remote IPC bus. Services can offer objects. Objects can have methods, and you can call methods, pass them input data, and or receive output data. There's a design decision that we made a long time ago that there's no classical separation between getter and setter functions, right? There's just methods that you can call. You can provide input JSON, you can receive output JSON. It's very implementation specific how the actual method works. Here's some examples. So on the bottom left, it's our system manager, procd. We can say ubus list system, and we can see we can get things like get our board, information about the board, reboot the device, handle the watchdog, do sysupgrade, do validation of a firmware image. This is a very basic example. On the bottom right, if we do ubus call system board, it will actually give us back a JSON telling us, what kernel are we running on, what version of OpenWRT is it, what's the host name, the compat string, that kind of information. There's a lot more complex stuff on UBus. So this is just a very high-level UBus list of a very simple OpenWT OpenWiFi configuration. You can see at the start, you've got your airtime fairness policies, you've got your host APD instance, DNS mask, the DHCP snooping, all your different network interfaces, wireless interfaces. There's the uCentral service, UNetD, which is our WireGuard VXLAN overlay, topology mapping, session management, service map management. Pretty much anything that you want to do with OpenWT is accessible via UBus. So Chris already mentioned this. So UCI is the Unified Configuration Interface. So Unified Configuration Interface is the three typical files that people will use as network, wireless, and firewall, right? So our three primary network config things. On the top right, you see an example. That's how the time server is, NTP server is configured. So you have sections which have a type, in this case, time server, and it's named as well, NTP. And then you have a list of options, right? So options are basically just key values. You can have lists of options, so it would be the list prefix. The reason is sometimes you want to have a named section to be able to directly address this. So network.WAN would be your WAN interface in your network configuration. You might want to specifically reference that. However, some firewall forwarding rules, you don't really care. You just have like your 5 forwarding rules. So those might be just type rules, right? Would be firewall and then, get me my first redirect rule. There's a very coherent, large documentation in the OpenWT wiki for all the base UCI settings with all the constraints, values, dependencies, and so on. The way this works is that the sys5 embeDD scripts, if you look at normal distributions, Linux distributions, you will find that a lot of the common open source services will have their own specific configuration file. We wanted to unify this. So the idea is we have UCI, and then on OpenWT, the embeDD scripts actually convert UCI into the service-specific configuration. That way we have a unified way of building, web UIs, or in our case, the OpenWiFi uCentral render model. Semantically, UCI files are like ini files, right? Been around for decades. And one of the cool things is there's a batch processing mode for UCI. So in the CLI, you can do something like UCI add network.WAN.IP address equal the IP address. What you can also do is you can build a file which just has set network.WAN.IP address equals something, set firewall.forwarding.destination equal WAN. And you can have a file of lots of these single commands, and then you can do an atomic operation where you basically say UCI batch, that file name. That's the feature that we actually do use for applying configs generated by uCentral. We'll get to that later on the slide. Yeah, so how do we tie all this together? So there's a thing called ucode. Ucode originally started up as a templating engine. So when we converted from Firewall 3 using IP tables and wanted to move to Firewall 4 using NF tables, IP tables uses IOCTLs to do the configuration of the kernel, which has been quite problematic in OpenWT land over the years, always been ABI and regression errors. So with the move to NF tables, Firewall 4, we decided we'll just do the table rules in text and use the built-in features of NF tables to apply the rule set that we've written into the kernel. To ease this, we wanted to build a Jinja-like templating engine, or the way Apache Tomcat works, where you can have a mix between standard out and your code blocks, right? I can have a code block, say for whatever, and then I have a text block, and it just prints out the text block. So this is what ucode became. It was the first version. Over time, we realized that we started actually building proper applications in it. So at that point, ucode got a raw mode, which was basically just normal procedural code without templating. And it was opt-in, and by now it's actually that the templating mode needs to be explicitly enabled, and ucode runs per default in raw mode, which is just a normal program, right? For those familiar with OpenWT, over the years we've used Lua a lot. Lua is a little bit annoying due to the way that the stack and the manual handling of the stack works. A little bit annoying with the C API. So This has got a lot of traction in the last few months with several of the core OpenWRT developers stopping to build small services in C or Lua and just using Ucode. There's some design goals that we wanted to achieve. So with Lua, we had the very easy handling of JSON. Right? As we saw with UBus, there's lots of JSON going on, so there needed to be an easy way of doing this. Okay, Ucode is actually very similar to ECMA version 7. So basically it's JavaScript syntax, right, with a few tweaks. So there's inherent native support for handling JSON data. We wanted the ability to, same way that Lua can do it, that I can build a program in C, and from that program in C very easily launch an instance of the virtual machine running the Ucode context. Yeah, as already mentioned, the templating capabilities and the ability to build, using a C binding, build new features that I can then call from within my Ucode, right? So in terms of OpenWiFi, what we needed to have the netlink 802.11 so that we can introspect the Wi-Fi state in the kernel, routing netlinks so we can modify switch behavior, ARP tables, neighborhood tables, all those kind of things. We wanted to be able to talk native UBus and UCI from within Ucode, so there's libraries or modules written in C which provide UBus and UCI APIs inside Ucode. And then obviously we have our built-in functions, right? So out of the box, Ucode comes along with your typical things that you would expect. We have handling for time, printf, standard in, standard out, signals, pushing, popping, splicing, slicing, merging, replacing, etc., arrays, strings, and so on. The usual stuff that you would expect. It's all there. So with our three components, UCI, UBus, and Ucode, we now have the primary building blocks that we need to interact from APNOS to OpenWRT, right? So UCI is how we send the configuration, UBus is how we communicate with the underlying operating system, and then Ucode is used to actually render out UCI and introspect the state using UBus. It's all JSON at the end of the day. The JSON then gets injected, comes either from the WebSocket, gets injected into this process, or the outcome would be our introspected state, which then as JSON data sent back up over the WebSocket to the gateway. So here's the flow of what happens when configuration hits the access point. So on the left-hand side, we can see the discovery of the cloud. This is what Chris mentioned with DigiCert, when the first contact daemon tries to do the first contact, find out who I talk to. Then we open up an MTLS socket to the gateway. We send our connect message, and we get our very first piece of configuration sent down. On the top right, we see the actual important pipeline, right? So the first thing that happens is gateway will already make sure that the JSON coming down is valid against data model, but we actually validate this again, right? So we have a piece of code called the reader. The reader will take in the JSON. It will remove everything that it doesn't know. It will reject everything that might be wrong. For example, we might have a Wi-Fi channel, and someone says, "Oh, I want the Wi-Fi channel 1000." Then the reader will say that's an invalid Wi-Fi channel. Or someone says, "I want to go on 640 megahertz bandwidth." We don't support that yet, so it gets rejected. That's what the reader does. So output is a pre-sanitized JSON where all the data types and data type constraints, min value and max value, are already enforced. That JSON gets pushed into the renderer, which we'll talk about in a second. We'll generate from the renderer the UCI batch files that we spoke about, write them to TempFS, apply them and reload the configuration. Unit comes up. The first thing the unit does afterwards is send a state message up into the gateway, and then the usual process happens. We send health checks, telemetry, state messages periodically, wait for new configuration, where basically green light came on, we're now in runtime state. Yeah, so the data model. Data model is written in JSON schema. Actually, we write it in YAML and then convert it from YAML into JSON. There are 5 primary sections, so there's global, interfaces, radio, services, and metrics. one of the things we have in globals, there's a section called definitions. In definitions, you can define your crypto settings, your radio servers. So if you have multiple VAPs with similar encryption or similar radio servers, you don't need to duplicate those settings inside your JSON. You basically just put it once in the definitions, and then you put a reference block into wherever you want to use it, right? So some design considerations we made at the time when we built this is we want this to be intent-based. If you look at the way OpenWT works with UCI, if you want to set up a captive portal, a very good example, you need to set up an interface in the network section, you need to set up the firewall rules. If you use UAM, you need to set up 2 web servers, one for the HTTP redirect, you need to set up another one on port 3990 for the UAM login URL. You know, there are multiple files that you need to edit. You also need to set up the Wi-Fi SSID, multiple files you need to edit, and need to make sure that all the pointers from one section to the other are all identical. We didn't want to have that inside the data model. In the data model, you just want to say, I want a captive portal, right? This is my Wi-Fi, I want a captive portal, just make sure it works somehow. Another design consideration is that we didn't want to write too much code ourselves, so the entire validation and reader code is actually automatically generated. There's a piece of U code which takes the JSON schema as input and outputs a huge piece of code which basically takes in the input JSON coming from the gateway, sanitizes, checks all the constraints, all the data types, outputs the sanitized version. Another thing is that we want to be hardware agnostic, right? So we don't care if your WAN port is ETH0, ETH1, whatever it's called. We just want to know there's a WAN port, there's a LAN port, right? So we can say, okay, LAN.star, I want to have an interface which uses all the LAN ports, or I want to use LAN2, use all the LAN, use the second LAN port. If it's there, it's there. If it's not there, it will send back an error saying there's no LAN2. This is what Chris mentioned earlier on with the error code 0, 1, and 2. So 0 basically means, okay, everything is fine. 1 means I applied config, but not quite the way you wanted it. I did the highest common denominator between what I can provide and what you requested. Here's the list of what I rejected, and then the error code 2 basically means, you know, there was like a proper error. I couldn't apply the config, try again. Same thing applies for Wi-Fi. So in Wi-Fi terms, we you can send a configuration for Wi-Fi 6 down to Wi-Fi 5 AP, which says I want to have HE80 applied. The renderer will then find out, okay, there's only, you know, 5 Wi-Fi 5 radio. I can't do HE, I have to use VHT. And I only have 40 megahertz, right? So it would basically say, okay, I'm starting the Wi-Fi on 5 gigahertz, but instead of using HE80, I'm using VHT40 because that's the maximum I can use. This goes along anything where we can kind of figure stuff out, same as channels. If you request a channel which might be valid 5 gigahertz channel, but you've chosen a country code where that channel isn't valid, it will say, look, you know, you've chosen a valid channel, but not for this country code. I'm using a different one. There are multiple strategies. So you can tell the device to then use automatic channel select or just use channel 36, right? So you can just default to like the first channel or automatically select one. Yeah, so here's an example of how simple configuration is. This is the entire configuration that we need to do for a captive portal that uses radius as a backend. So on the top we see we have an SSID entity. We create one. We say the name is OpenWiFi hotspot. We say we want this to be on 5 gigahertz. This is an array, so we can say 5 gigahertz, 2 gigahertz, 6 gigahertz. Would actually spawn 3 of them. And then there's the array services, and we say, okay, we want to run the service captive portal on this SSID. Further down, we have a section, a dictionary called services. There would be other ones in there, like the SSH server, MDNS, LLDP, whatever you configure. In this case, it's radius. It's captive portal, and we choose the authentication mode radius and say this is our auth server. So in this case, when the user connects to this SSID, he would get presented with a local credentials login page where you can put username, password, which gets validated against radius. On the right-hand side, there's a tool called JSON Schema for Humans, I think it was, which converts your JSON schema into an HTML file, which you can click around, pops up and closes, and you can see all the different constraints, all the different versions and data types and so on. So that's online as well. Here we see the specific schema definition in that online page for that services section. Yeah, render templates. So on the right, we see the output from a render template for SSH. This is the UCI batch which I was talking about. It's just a bunch of UCI sequences, and we can run the UCI tool in command line and have one atomic operation to apply all those things. You will find that when a complex configuration gets pushed down to the device, the renderer will actually generate a file with several hundred of these lines. Once it's done, we apply it, new config comes up. The entire renderer is implemented in Ucode. Although JSON schema allows us to do complex dependency logics directly in the schema, these can become very tedious to maintain and write. So we have some basic stuff is in JSON schema, some more complex stuff we actually do in Ucode. An example for this would be management frame protection, for example. So this would be the function where we work out what kind of 802.11w management frame protection we have to do. There are certain Wi-Fi encryption modes which require to be enforced or optional. So all your 6 gigahertz, your SAEs, your WPA3s and so on, they actually require you hard to enable management frame protection. All your SAE3 mixed modes, they have it optional. And then obviously if you have no encryption, then we force no MFP. If none of the specific corner case requirements get hit, then we just use what the user told us to use. So renderer is a huge collection of many different scripts. So we try to have scripts of only 40, 50 lines maximum. Each one of them is for one single intent. We have one renderer for how to render an SSID, how to render a VLAN, how to render a DHCP section, how to do a captive portal, and so on. There's a file called top level, which is the very first file when the renderer gets spawned, that gets called, and it loads a special file called renderer, which is essentially a class. And this class has a pile of helper functions, right? So as I said earlier on, we don't care if the physical network interface is ETH0 or ETH1. For us, it's a logical interface, but we need some kind of way to handle, to do the lookup of the names of which ones to use. So that would be our lookup of network interfaces. We want to track VLANs. So in reality, because we use the Linux kernel's bridge VLAN filtering functionality, which means that even if your logical interface doesn't have a VLAN, for us, technically it still does have a VLAN. We just assign a random number that isn't used by any other device and just make sure that traffic isn't tagged, right? But we internally inside our bridges still track stuff on virtual VLANs. Routing tables, right? Sometimes for policy-based routing, when you have multiple VLANs or metrics, you need to be able to dynamically grab a routing table. The renderer class will take care of this as well. There's also file storage, so sometimes we might, for open roaming, we might want to have the icons that are presented to the user to be pushed down. Those don't need to be persistently stored, right? We need some way to transfer them, however. So we can basically say, hey, I just want to have a file for the lifetime of this very specific configuration. Once the new configuration comes along, just delete all those files, and I don't care what it's called. Just randomly generate a name, tell me that name, and I can then use that name inside my Wi-Fi configuration where I use that. I can just say, look, there's an icon somewhere, don't care, that's where you can find it. There are two additional helper macros, which is B and S. They just do basic sanitization of Boolean and string. So when we write a Boolean value into UCI, the input could be true, false, null, an empty array, whatever, and the B macro basically makes sure that the outcome is always 0 or 1. String sanitization just makes sure that we have the according escape sequences in there, right? So that, imagine you have a string which uses some of the special, hyphen syntax used by UCI files to mark the beginning and the end of a string. If you have that inside the string, it needs to be escaped, special characters as well. So that's what the S macro does. Yeah, so an example would be, I want to run an SSH server. So there are 3 things that we need to do. We need to, first of all, enable the SSH server. That would be, which port am I running on? Am I allowed to do password auth? We need to possibly store the authorized SSH keys, and we need to configure the firewall. So this is what the entire template looks like. You can see the Ginger-like templating, so the top block is actual code. Anything inside the curly brackets is executed as raw U code. Anything outside is just pushed into standard output. You can see in these lines here, you can see the double curly brackets. That basically means in our standard output templating context, we can inject the value of a variable. In that case, you see the B and the S macro. So what does this do? The first thing it does is it asks the renderer class, tell me all interfaces that use the SSH service. And then if there are none, then disable the SSH server. Otherwise, write any possible authorized keys. Then we set three UCI options. One is enable the service. Second, which port to run on. And then am I allowed to use password authentication or just key authentication? That's pretty much our SSH server already configured. And the second block is just a loop around all interfaces, which sets up one specific input rule on the firewall saying on this interface, port in most cases 22 TCP is now allowed, and I'm accepting incoming connections. Yeah, so we run lots of these templates. Temp ucentral.uci is generated. We use UCI batch on that file, UCI commit, reload config. It takes a couple of seconds, unit comes up, everything is reconfigured. First thing we do is then send a message to the gateway saying, this UID of configuration has been applied, error code is 012, and here's a JSON dictionary of all the rejects or problems or warnings or errors that we found, which in our case could be something like, wrong HT mode, wrong channel. If you say configure 6 gigahertz and the unit doesn't have 6 gigahertz, it would say I couldn't find a matching file for that configuration. Yeah, so we now looked at data coming down from the gateway going to the device. What goes up from the device to the gateway? So the first thing is a state message. A state message, same as configuration, has a predefined JSON schema. We periodically push this, aggregated state. This is inside the data model. You can configure it. Default configurations, I think, 120 seconds. So every 120 seconds, we send up the delta from the last time that we sent this. So it would be system utilization, what's the CPU load, how many processes are running, how much memory is used. We go over all the interfaces and say, these interfaces currently traffic counters, how many clients are connected, neighbors, ARP tables. With Wi-Fi, we would send the channel noise, channel load, current TX power, all those kind of things. Clients, all the IPv4 and IPv6 configurations of the clients, and then obviously our additional services, right? Any service will have a state, LLDP, ARP, neighborhood tables, and so on. You will find that the state.uc, the script is about 800 lines. The first 400 lines is just a bunch of UBus calls, and then we have two big loops iterating over all of this and sending up the JSON. The second thing happening is health check. So health check is also periodic, where we scan all local and remote services, as in DNS, DHCP, radios. We check if the device is online. We have a list of 20 checks that we do, and based on that, how many of those are successful or failed. We build a score between 0 and 100 and send that up, and that's kind of how healthy is the device right now. And then the last thing is telemetry. So telemetry is a almost real-time thing, so we can send telemetry as low as every 2 seconds. The device will use UBus, pub, sub to gather events, right? And then the default configuration is send up the events when the buffer is filled to more than 1,000 events, or if your periodicity of 2 seconds, 4 seconds, 5 seconds has expired. So we aggregate everything into one big message, send it on the WebSocket. So right now this would be DHCP, any kind of DHCP frame that we sniff, wireless management frames. Extending this is very simple. Anyone who does pub sub on UBus can be simply added to just a list of these are the publish and subscribe endpoints or objects that we want to listen to. Yeah, and then finally we can get commands sent down from the access point to the device, from the cloud to the device. So there's three main categories. So one is system maintenance, would be upgrade, reboot, factory reset, and then forensics, which would be traffic captures, wireless scans, and so on. And then for debugging, we have the ability to send down scripts which can gather extended data. So there's a project going on within TIP called the application-specific bundle, which kind of tries to formulate a predefined way of gathering data for technician debugging. Yeah, OpenWRT will provide three different images. One is this upgrade image. This is when OpenWRT is already flashed and you go from OpenWRT to OpenWRT. There's factory images. Those tend to be the takeover images. So if the device comes from your vendor and has like QSDK or whatever installed, you can go and migrate to OpenWRT. And then for developers, obviously, you have init RAMFS, which are bootable from RAM. They reduce turnover time during development. Yeah, this is very developer specific. We spoke about this earlier on. This is very typical in OpenWRT. You have a folder for a specific package. It has a make file. Again, defining the repo that you want to pull the code from. You have your patches, your source, and then any additional rootfs files that you need to bind the service into your OpenWRT file system. Very typical OpenWRT makefile, also two sections. Top sections, just variables defining where to load the code from, license, maintainer, and the bottom half are the actual CMake build templates describing. The first one would be the configuration template, which describes a menu config, where to list stuff. Then you have the compile template and the install template. So there's built-in support for multiple build systems, so there's CMake built in there, there's automake in there. In case of CMake, you configure and your actual make or compile target will always be the same. So if you just say include CMake, then you don't need to define what you compile and what your install looks like, because it's just already handled by CMake. This makes writing and porting new applications into OpenWRT very trivial and very easy. Yeah, dry theory. So Git. I could spend entire talk talking about Git. If you play around with patches and OpenWRT or Linux in general, any open source, this kind of stuff, you need to be able to do this automatically. This needs to be finger buffer memory typing these commands. Here's a short overview of how to check out a branch, how to create a new staging branch from that, then you edit your files. As we saw earlier on, this basically always involves editing either a make file, adding or removing a patch, adding or removing a file, editing or removing a piece of source code. You made your changes, you do git add, you commit it. Thing to watch out for, which quite commonly is an error that people make, is that the actual annotation of the patch is incorrect. So you want to have their very typical ways in open source how patch annotation works. It's always advisable to just do git log on a package that you're editing to see what have the previous people in the last 5 years or 10 years done and what's the format of patch annotation. And then obviously there's the DCO. That's one of the most important things. That's the developer certificate of origin. And DCO basically means it's your signed off by. And it basically means that the developer who's contributing this change is saying that yes, I'm allowed to publish this as open source and you're allowed to include it without infringing any kind of copyright and or similar. Yeah, once your patch is ready, you push it to your branch, you go to GitHub and you see the big green button that everybody loves. You hit the button, you're good to go. Again, make sure you signed off by is set. Yeah. And there are plenty of really good examples inside Git OpenWiFi, inside GitHub, of people trying to use this. And it's always a good idea to go online, check out previous changes made to a specific repository. It gives you a very good indication on what kind of format people expect from you. Okay, this is the really interesting part. Everything up to now was dry theory. So these are containers. It's unfortunately a little bit small. What you see on the bottom right is someone just logging into an OpenWRT. He does UXT list. We can see there's an Alpine container running. Then we check the volume manager. Oh, there's a volume called Alpine, right? So the first things we do for this demo is we kill the Alpine container. And then we recreate the Alpine container. And then we say, start the Alpine container and attach the console. So now, running next to, on this very kernel, running next to the OpenWT userland, we have an entire Alpine Linux running inside a OCI conforming container. This is running on a device which has 4 gigabytes of eMMC, so there's 3 gigabytes available. And we can do an APK update, which means we have full network capabilities inside the container. Due to the way OCI works, we have C groups. We have def firewalling, anything Linux capabilities, seccomp, and so on. So we can build containers that have networking or don't have networking, that have native networking or have to use the VFETH virtual pair tunnel to actually get online. It's all possible. Anything pretty much inside OCI is supported and can be done here. So these are full-scale file system containers. We also do slim containers where we use LD preload to enforce seccomp. Basically means anything running on the system right now. We use this a lot in OpenWT for things like DNS mask, host APD. We basically say any network exposed service, if it gets hacked, then nothing can happen because the service can't really do anything anymore. So container lifecycle management. Containers can be managed independent of the actual host operating system. They can be restored and removed, updated. From an OpenWT perspective, this is just a package, right? The same way I can say install a web server, I can say install this container. Advantage is that the container can have a dependency on the OpenWT package. Let's say you install a container that has some Bluetooth feature in it. You can actually make it install the Bluetooth kernel module on the host system before spawning the container. You can also update the host operating system, so we can have a container installed for some feature, Bluetooth, some VPN or torrent or whatever. We can update the OpenWT or OpenWiFi system, and the container will actually stay consistent or persistent with its configuration. To be able to do this, we have a thing called storage volume management. So when a new container gets installed, inside its configuration, OCI would actually say, look, I need to have a read-write volume, a read-only volume, this is how much space I need. And then the storage volume manager will actually work out what kind of storage is actually on this device. Is it NAND? Is it proper HD? Is it eMMC? Do you have an SSD and SD card, whatever? And then depending on what kind of storage it is, how big the storage is, it will figure out, do I need to use UBI volumes with UBIFS? Do I use X4, FS2S? Just figure out the best solution, automatically create the container for you, and during boot it will actually automatically mount these containers. So there's kind of an auto mount, auto run feature for our containers. But it's all inside our configuration, right? We can basically choose, I want to manually start this container, or this container should automatically be started as part of our OCI configuration. Yeah, classical BPF, so Berkeley packet filter. Bottom has a good example, so pretty much everyone's used this who does Linux CLI stuff. TCP dump minus ETH0, port 53. So the port 53 filter, that's actually BPF that gets sent up into the Linux socket. BPFs get converted into virtual machine bytecode. They get uploaded into the virtual machine inside the kernel, and then every packet on that socket will run through the virtual machine code, gets validated, and either dropped or forwarded into userland. Extended Berkeley packet filter. So there's been a lot of work going on with packet filter. So eBPF is a VM inside the kernel which implements a RISC-like assembly. The kernel has a so-called validator or syntax checker. So if we upload something into the kernel, because it's running in raw kernel mode, we need to make sure there are no endless loops. So there are certain constraints in what a BPF program can do. Once it passed the validator, it actually gets compiled using a JIT compiler into native CPU code and gets executed. So this stuff is like ultra fast. The way it communicates with userland is there are maps, and you can have multiple types of, there are different types of maps, you can have any number of these maps. There's a very good presentation from someone at Facebook explaining how Facebook uses this internally at Facebook. It's pretty cool stuff. They mainly use it for tracking down issues, crashes, program errors. You know, the more complex your system is, the more weird issues you actually run into over time, and tracking them down can be quite cumbersome. Yeah, so this is high level how BPF works. You have your input on the top left, your BPF program, which is normally written in C, gets compiled into bytecode, gets loaded into the kernel. Kernel runs the verifier, generates the native code. Yeah, and then from inside the native code, when it gets executed, there are certain kernel functions that you can call, like, for example, handle trace points or K probes, or work with network packets, forward a network packet to a different interface, and so on. And then obviously you can talk to the BPF maps. BPF maps are just key value stores, essentially, right, that you can write data to. And then normally you have a user space component. In this case, this would be the reader, and the reader can talk to the maps, populate and read out state, so there's a bidirectional communication possible. So yeah, what is eBPF used for? I mentioned this, so observability, trace points, and perf events. This is what Facebook uses in its infrastructure group quite a lot. You have security, so BPF, even in CBPF days, was used quite a lot for firewalling. There's been recent changes in C groups where we can use BPFs to dynamically scale a control group behavior of a kernel or hardware based on thermal sensors, for example, right? So we can say the maximum CPU load can be throttled down to a certain value if the temperature of the CPU goes up, right? So it's a little bit more performant and efficient than the CPU load governors that we normally use. And then obviously the big task for us and a lot for Meta is networking. So networking, Meta or Facebook has a thing called Catran, which is an L4 load balancing redirector thing. Pretty much the entire underlying network of the infrastructure of the entire platform runs on this thing, and it's written in eBPF. There's also P4, which is a programmable switch, which Meta is quite active in. And then with OpenWiFi, we use it for quality of service and our next-gen captive portal. Those are the two biggest applications that we have. Yeah, so Quasify, if you've been up in the Meta booth, there's screen explaining how Quasify works, how we use DSCP tagging. We do network segment filtering, so we use that for IoT networks, parental control, captive portals. There's a thing called Bridger, which we'll skip for now because it's a feature for very new kernels that do NF tables flow offloading in hardware, which there's only one board right now that's not commonly used that actually does this, but it supports it. And then we have the MSS fix for accelerated path MTU discovery. So let's look at some of these in detail. Yeah, so Quasify, dynamic DSCP marking of packets. The idea is that we have certain rules based on which we set the DSCP mark of flows or packets, right? So this can be protocol, port, DNS that we're going to, IP address, or even flow behavior, right? So we have flow-based behavior detection for bulk and priority traffic. An example would be traffic going to PlayStation Network would be priority traffic, but then suddenly the PlayStation downloads the game and generates 30 gigabytes of traffic. We automatically detect that this is bulk traffic, we'll deprioritize it, and then once the bulk traffic is gone, anything going up into the PlayStation Network afterwards would be priority traffic again. DSCP now comes out, hits our network wire port, and then fcake, fqcodel, diffserv4 run, usual setup, and DSCP marking drastically helps it. So in some of our measurements for real-time gaming, we've seen latencies drop from 100 milliseconds to 30 milliseconds. Voice over IP also drastic drop, and in general, specifically under load, even session initiation, if you go to Zoom or something, it's a lot faster. Like it's more responsive from a user perspective. This also ties into wireless multimedia UP classes using QoS maps on Wi-Fi. So anything that we classify ingress actually hits the according quality of service class queue on the Wi-Fi. And we support asymmetric tagging. So when we do tagging, there's a possibility to not say use this DSCP tag, but use a name, because we know that on our Wi-Fi, voice over IP traffic or real-time video traffic one tagging might work better on our Wi-Fi, but our upstream ISP might require something else. Yeah, so here's a flow chart. Due to the very small screens, it's probably hard to read. Basically explains the different steps when a packet comes in, how we do the port lookup, how we do the flow-based hash lookup, and then all the fallback modes, figuring out if it's a class, if it's not classified, do we want to reclassify it if it's already classified, and so on. On the right, we see a typical configuration file. This is the default example configuration file shipped with Quasify, which basically just makes sure that any DNS traffic is network classified. SSH is interactive, NTP is network, and then any kind of HTTP, HTTPS, and QUIC is best effort traffic. Yeah, unit ACL. So unit ACL is our port segment, network segment filtering tool. This is what I mentioned earlier on: captive portal, IoT access networks, parental control. It has the ability to look at traffic generated by stations, assign behavioral classes to the MAC addresses, and then based on which behavioral class the MAC address is in, certain kind of behavior of the traffic. So any number of rules can be applied to a class, and these could be things like set a firewall mark, do a redirect, insert, remove a VLAN, change the egress interface. And this basically allows us, in combination with certain firewall settings, to apply DNAT rules for clients inside captive ports which haven't been authenticated, or allow DNS snooping to whitelist certain domains so that we have a walled garden for a captive portal for things to be able to go online. Yeah, so this is our typical configuration for hotspot. We say the default class is 0 DNS because we need to be able to allow DNS traffic even for non-authenticated clients. We say the default class for DNS is different to the other one, so it's 1. And then we have our two classes. Class 0, unauthenticated traffic, basically, such as says DNAT all the traffic to our local interface. And authenticated traffic just sets a specific firewall mark. The idea behind the specific firewall mark is that we need to be able to expose the HTTP 3990 UAM port to any associated client. And then on the bottom we have a list of DNSs. So if a client tries to connect to a snooped IP from one of those DNSs, automatically gets into the authenticated class even if the client isn't authenticated. So here's an example of PWM Vani using this. So one of the big problems that people had with Kuva, especially in bridge mode, is performance. So you were seeing that even on powerful devices, it was hard to reach anything above like 60, 70, 80 mbit. So this is a client on an AP behind a 250 mbit GPON uplink. So it's just connected, and then we start speed test. And we can see that it almost instantly hits the 230 mbit mark, right? So we've run this test on faster uplinks. The laptop that I was using maxes out at about 600 mbit, and I was easily able to reach this without the CPU even hitting like any bottleneck, right? Because eBPF is virtually free. Yeah, MSS fix. So one of the things that we were seeing is when we do a WireGuard VXLAN overlay tunnel and do traffic, specifically www traffic over that, the MTU discovery simply is too slow. And then loading certain pages that don't, when the server on the other end doesn't do proper PMTU discovery or window size adjustments in TCP, sessions simply wouldn't load. TCP and HTTP traffic would just hang. So we spent some time thinking about this, and we have a small BPF program for this, right? So, on the top, that's our typical network header, and there's a flag. And what we do is inside SYN packets of HTTP connections or TCP connections, we work out the maximum possible free space that we have, and we simply patch SYN packets to include the MSS fix. And by doing so, it's instant, right? During TCP establishment, both sides automatically know which window size and which MTU size they're on. Normally, PMTU discovery will use ICMP, and it's simply too slow, right? It simply doesn't work. So another great use case for BPF. Yeah, so a little bit of theory on Wi-Fi. So in the classical days, we had a differentiation between softMAC and fullMAC. SoftMAC meant that the entire protocol handling was done in software by Linux. FullMAC meant that you had a firmware loaded into your wireless Mac, which did the entire 802.11 stack. So a classical example of this would be Broadcom FullMAC. The driver is actually called Broadcom FullMAC. Same silicon that you will find inside your iOS devices. So iOS or OS X doesn't actually have a Wi-Fi stack. They fully rely on the Wi-Fi stack inside the Broadcom Wi-Fi's firmware. Companies like Qualcomm, MediaTek tended to have softMAC drivers, which means that Linux actually handles all the TX management frame handling, right? Nowadays, there's kind of like this hybrid due to the high data rates, Wi-Fi 6, Wi-Fi 7. Certain features require pseudo real-time, so those features need to be offloaded into the Wi-Fi firmware. So you have kind of like this hybrid mode. What we generally say, if management frames are handled by host APD and the kernel, we still have softMAC, even if some of the features might already be offloaded in hardware. Otherwise, we have fullMAC. There are three main components. So Netlink 802.11 is the ABI that we use in key value pairs to talk to the kernel. Config 802.11 are so Netlink is the actual transport formatting or framing. Config 802.11 is then the namespace of all the attributes that we can send, like set an SSID and so on. And then we have two versions of drivers. A softMAC driver will use Mac 802.11, which is the kernel's 802.11 implementation, or in case of Broadcom FullMAC, it will sit directly on config 802.11 and not use the kernel's 802.11 stack. Yeah, Linux MLME is split up into two parts, userland and kernel space. Host APD one of the examples of offloading would be the kernel the beacon templates. So beacons need to be sent every 100 milliseconds pretty accurately, sometimes even faster, but 100 milliseconds is, sweet spot that everybody uses. So instead of sending it every 100 milliseconds, we basically build the template, send it to the kernel with some offsets of where CSA happens and so on, and just say, please broadcast this every 100 milliseconds. When certain management frames, like ASOCs, probe requests, auth requests, and so on, get received by host APD, they get bounced into userland, host APD processes them and then builds the reply. This is also the frames that we pick up and send up in telemetry. Mac 802.11 does certain other things like handling stations. There's a little bit of rate control going on, but as I said, most of the stuff nowadays, rate control is done in hardware or in firmware. There are certain types of interfaces, so the most common ones are access point, obviously. As I said, beacon templates are done by host APD. We have station interfaces. TIP uses those for onboarding. There's a mode in TIP where we can have hidden APs, hidden SSIDs on our APs called OpenWiFi onboarding. They utilize the TIP-specific DigiCert certificates. So a unit can come up, and if it can't get wired connection to anywhere, it can actually try to use a Wi-Fi station connection to another OpenWiFi access point using its TIP certificates to authenticate using EAP TTLS. Goes online. So we use station interface. Then we use mesh interfaces, 802.11s, but only the actual MAC layer, not the forwarding algorithm part, and then AP VLANs. So due to the way that Wi-Fi works, there's no VLAN concept, right? We want to have a bridge interface with a VLAN, put a Wi-Fi into it, but we don't really want to transmit the Wi-Fi, the VLAN tag inside the frames over the Wi-Fi, right? So Linux has this thing called AP VLANs, where you have an AP interface, and then if a client connects on a specific VLAN, it will spawn an extra network interface. So if you have WLAN 1, it would spawn WLAN 1.100 would be your VLAN 100. but the actual traffic on the interface wouldn't be tagged. This is how our dynamic VLAN works. Chris spoke about this early on about Whisper, radius-driven dynamic VLAN, and so on. And then obviously there are your P2Ps, IBSS. None of those are supported right now by OpenWiFi because there's no real-life scenario where we need them. Yeah, mesh. So we spoke about this. We use 802.11s. We don't use the forwarding algorithms, right? We use Batman for this. Batman is a L2, A3 routing algorithm. There are algorithms which are better for larger area L2, that would be Babel. Batman is more for your local 30, 40, 50 AP setup. Yeah, it's essentially a standardized replacement for WDS. We could even build this with WDS, but with WDS you have a lot of traffic duplication, and you don't have any loop detection, right? So Batman has inherent loop detection inside it. Yeah, another important thing to mention is rate control. So transmission happens on MCS, NSS, channel width, right? So if the rate is wrong, you send at a too high rate, high data loss. If the rate is too low that you send at, you get bad throughput. So, there's an algorithm trying to figure out what's the best rate that I can use to send with the least data loss, yielding the highest quality of throughput at the highest possible bandwidth. The transmission rate, bandwidth, channel number, antenna number, and so on is determined by rate control. So in Linux, Minstrel used to do this. Then we had Minstrel HT. There were some changes to Minstrel HT to utilize, the new multi-MIMO, Wi-Fi 6, and so on. With Wi-Fi 6, 6E, Wi-Fi 7, what we're seeing more and more that certain rate control decisions are offloaded to firmware because it's just data rates are too fast and the rates need to be adapted too quickly for userland or kernel space to actually pull out all the data, process it, and then work out the new rate and push it back. The turnaround time is simply too hard for that.
Is that configurable?
Hmm?
Is it configurable like the algorithm, or is it just, it is what it is?
Yeah, so the question is if the rate control algorithm inside the firmware is configurable. It's not. So we've been having discussion with some of the vendors that not just that it's not configurable, but we have absolutely no introspection. We can't even find out what it is. Same with transmit power control. The firmware does something. Airtime fairness is another case where the firmware just does some airtime fairness and we can't even get the metrics out, let alone configure it, right? So we're not even being greedy, want to send parameters to define the behavior. Is just simply knowing what the thing does would be cool. There are two types of vendors. On one kind of vendor, yeah, it's all possible, and the other ones are all completely locked down. There's no in between, right? But it's an ongoing discussion that we keep raising in meetings with these vendors, maybe one day. But this isn't even like an OpenWiFi specific problem. This is, even if you use like the SDKs from those vendors, same behavior, right? This isn't like, it would work if you use the proprietary driver. No, the proprietary driver actually has less features in that aspect. We already have more than they do. Yeah, to summarize, we could talk about a lot more things, right? There are several features which we skipped, right? Especially with eBPF. There are more things where we use eBPF. We could have talked about like the entire onboarding and so on. Yeah, final sentence. We have our weekly stand-up meetings. Anyone is welcome to join the weekly stand-ups. Slack, dev calls, community participation. Any kind of ask that we get, we are always listening. A lot of the ideas that we have come from community. Quite often the final solution looks slightly different because community might provide a solution. Well, we try to understand the problem and find a more generic solution that possibly fixes other problems as well. But we are always more than welcome to listen to any idea and try our best to incorporate it into the firmware. And I think that sums it up. Thanks. Okay. Yes.
We are developing applications on top of OpenWiFi, OpenWRT. one of the things that came up recently, we're trying to port a non-SQL database, MongoDB, on OpenWRT, and running into some issues. Have you had any experience with that?
What kind of database?
Oh, MongoDB. It relates to OpenWRT, I believe. No.
Run into this problem.
Yeah, no, as you mentioned, Mongo, the first thought I had that came to mind was as perhaps the back-end persistence that the gateway would rely on instead of Postgres, which is entirely possible. That would be an ORM logic change at the microservice level. So that's definitely possible, but I'm not even sure I could think of an example as to how it might.
So if you want to install
Tied to
MongoDB
WRT.
directly on OpenWRT, it might just be a problem with the current build package or the architecture. So in those cases, if it's just an OpenWRT problem, go on the forum, go on the mailing list, just describe the problem, and there's an open source community. You tend to have people answering quite quickly on these problems. Try to figure out from the makefile who the maintainer is. Just send an email to the maintainer directly, add a comment on GitHub, raise an issue on GitHub. There are multiple ways of contacting the maintainers.
Okay.
Yeah.
Thank you.
Sure.
Any other questions at all for John?
Hello, John. I have a stupid question, I think, but why are you using OpenWRT instead of LIDI, for example? I think it's the same project at the beginning, or
Instead of what?
LEDE or LIDE or LEAD.
Oh no, so there's LEAD doesn't exist anymore. So LEAD was an interim reboot of the OpenWRT project to sort some internal infrastructure problems. So LEAD was essentially 2015 was the last OpenWRT release, 2017 was LEAD, and then with 2019 the two projects merged back together into OpenWRT. And then since then going forward it's OpenWRT again.
Okay. I have another question about the telemetry. I think you talk about telemetry. Can we have events that are triggered by this telemetry to send, I don't know, to make things happen in the APIs or things like that, triggered by the telemetry that we have in the controller?
Yeah, so inside the controller, you can have a microservice, for example. This is what RRM does, the RRM microservice. It takes telemetry, makes decisions based on that. It can send commands down to kick clients, to roam clients. Yeah.
But
so
we need to configure it in the control. I mean, how do we script the feature in the controller? I mean, if we want to do something, how do we? Can we run a script or something?
yeah, so there are multiple ways. Either you can have a microservice to do this, or you can just have a script which just constantly pulls data from Kafka, and then sends over OpenAPI any command that you want to the AP.
Okay. And I have the last question. Sorry.
Sure.
About the captive portal that you talk about. I know we were talking about profiles, iOS and Android profiles. Can we just load these profiles into the captive portal to make that we download this?
No. So the problem with you mean open roaming profiles, right? Yeah. So the problem with open roaming profiles is that inside the open roaming profile it points at google.com, orion.google.com or whatever.
Ah, yes, sir. I have
And then they actually will enforce that it's downloaded from that specific FQDN or file server.
Yes.
Right? It's a security thing. Otherwise, I could go and say, okay, I'm now installing a certificate from myserver.com for Vodafone.com.
Yes.
Right? I can just create any profile and just say, oh, I'm a Vodafone now.
Yes, you're right. We talk about the certificates. Yes. Oh, thank you.
that's why
Thank
you
you very
have to-
much, John Chris.
Sure. Okay.
John, thank you so much.
Thank you very
And
much, Chris.
John, my personal thanks to you and the team that you drive at embed. The firmware stack is just tremendous what's happened here for OpenWiFi, so thank you kindly
Thank you very much.
for all you've done.
Thanks.
Thanks everyone for attending.
Thank you.
Cheers.